hurricane bears down on the Gulf Coast. It is a monster, hundreds of miles wide with winds of 150 miles per hour.
Oh my God. Oh, wow!
Scientists race to predict where it will go next. To do that, they fly directly into the dangerous heart of the storm. But as climate change looms, even more frightening questions come to light. Are hurricanes getting stronger?
Really, really bad here, folks.
In the future, will these killing machines pack an even more destructive punch? Sophisticated new tools are ripping the veil of mystery off of one of nature's most powerful creations, giving scientists a look at the inside of the machine. It's a race to piece together the puzzle of exactly how nature does its work, engineering hurricanes. Every hurricane offers scientists a chance to learn more about how these storms work. August 2008. Hurricane Gustav is the third hurricane in 3 months to threaten the southeast. Now, 250 miles wide with gusts of wind nearing 150 miles per hour, this monster storm is propelling itself through the Atlantic on its way to the U.S. Gulf Coast. And the Army Air Reserve hurricane hunters are heading straight into it. Major Brian Schroeder is the unit's weather officer. He's going to get them into the heart of Gustav.
To get really at what goes on inside a storm, we need to fly through these storms to collect the weather data.
They want to figure out how this hurricane is put together and what it's doing. Is it growing stronger? How fast are the winds? And the big question on everyone's mind, which way will it turn?
All of the forecast models have it hitting somewhere near New Orleans or slightly to the west of there. Of course, as time goes on and as this system moves into the Gulf of Mexico a little bit more, all of that could change.
Gustav is large, powerful, and hard to predict. It's like a gigantic machine with a lot of moving parts, all moving fast. But where does a monster storm like Gustav come from? The seeds of all hurricanes lie in gentler winds that constantly circle the Earth.
The wind is created by an unequal distribution of pressure on the surface of the Earth. Now, we tend to get low pressure where warm air is rising over the equator, high pressure over the poles where the cold air is sinking. And this air wants to flow from the area of high pressure towards the low pressure. This is what creates wind in the atmosphere.
So colder, high-pressure air rushes in from the poles to replace the warm, low-pressure air rising over the tropics. The winds collide near the equator, where they are forced straight up, drawing warm, moist air away from the surface and up into the atmosphere. This is the Intertropical Convergence Zone. This is where hurricane assembly begins.
It is a very unique location because it's very persistent. Now, 24 hours a day, 7 days a week, 365 days a year, there's always this belt of storminess around the equator.
Throughout the summer, towering thunderheads form here. Hurricane parts, just waiting for a power supply to kick them into action.
The ocean waters are very warm because they've been heated by the sun. Now, as the air that's in contact with this warm water acquires the heat, and then the warm air wants to rise upward, this is called convection. Keep in mind, this warm air also has a lot of water vapor in it. And as that air rises just a few thousand feet, it begins to cool off, and that leads to condensation. So that's why clouds are associated with this convection over the equator.
The converging winds and tropical sun produce conditions almost perfect for hurricane creation.
The intertropical convergence zone provides a lot of the necessary ingredients to get a hurricane going. What we still need to get going is rotation.
In the Atlantic, the spin power comes from the hot winds blowing across Africa.
An African easterly wave is a belt of fast-moving wind that gains energy as it moves across the continent of Africa. If you allow this belt of wind to begin interacting with mountains or terrain features, sometimes the belt of wind can be disturbed, and it can form little ripples or little eddies.
Every few days, hot winds ripple off the African coast. They bump into the storm clouds sitting in the tropics and start the clouds spinning. Now, they begin to move and turn in a more organized band. If they get organized enough, they become a tropical depression. And that's how the hurricane building process starts. The technical name for this kind of storm is tropical cyclone. Hurricane is what the storms are called in the North Atlantic Ocean. But it's the same process around the world. Cold air meets warm water at the equator, supplying the raw materials to build these destructive machines. Off the coast of Japan, the warm winds over the Pacific Ocean create storms called typhoons. In 2007, Super Typhoon Manyi pounded Japan with 145-mile-per-hour winds. It was the worst storm to hit that country in more than 50 years. In the southern hemisphere, the storms that hit Indonesia, New Zealand, and Australia are simply called cyclones. In March 2009, Cyclone Hamish only grazed the north coast of Australia, but still hit with 12-foot waves and 145-mile-per-hour winds at its peak. No matter what they're called or where they form, all these storms begin as tropical depressions, but very few tropical depressions grow to hurricane strength.
If you have all these little rotating early disturbances, why do you have so few of these intensifying to hurricanes? Well, that's the million-dollar question right there.
It's a question that drives researchers like the hurricane hunters into the heart of these storms. And Gustav is one more opportunity to find an answer. On August 30th, the hurricane hits a small island off the Cuban coast. Winds are 150 miles per hour, almost a Category 5, the strongest type of hurricane there is. Will it get even bigger and stronger? The hurricane hunters are trying to find out. To do it, they need to measure two key elements, one that's a hurricane killer and one that's fuel for the hurricane's engine. The first is called wind shear, strong cross-cutting winds at high altitude that can cut or shear off the top of the storm, tearing it apart.
If there's no winds at mid or upper levels that are going to impede the storm's movement as it moves along, the chances of that storm surviving and getting stronger are pretty high.
The plane's radar detects very little wind shear, the perfect condition for Hurricane Gustav to get bigger. The other measurement is water temperature. Warm ocean water is the fuel, the source of energy that drives convection up into the storm. Convection creates low pressure, and that helps build hurricanes.
The warmer the ocean temperatures are, the more convective activity we're going to see. With more convection, and you're going to have a stronger hurricane.
To find out just how much energy the warm water is providing, they have to read the temperature from inside the hurricane. For that, they'll use a disposable device called a drop sonde. It's an instrument package they drop into the storm.
This is a drop sonde right here. This is collecting temperature as well as dew point temperature. It gets the wind speed off of just the wind going through the sensor here, and then it sends a GPS signal back to the aircraft so we can track it. So that's how we know what the wind direction is doing.
The drop sonde is launched directly into the storm. After it's launched, a parachute opens to slow its descent. As it falls, it sends its temperature, humidity, and pressure readings back up to the plane. Combined with the wind shear readings from the plane's radar, the drop sonde data gives a clear picture of what's going on inside the hurricane. With minimal wind shear and enough warm water, a storm like this can become something much bigger. The hurricane is an ocean-borne phenomenon. This is where the raw materials of the wind, warm water, and rain clouds come together to grow these spectacular storms. This also makes the ocean one of the first places that scientists look to monitor the storm-forming conditions.
Today we're going out, we're setting this 3-meter buoy out at Ambrose Station, 12.5 miles off the port of New York.
Once in location, the buoy starts sending its readings back to the NOAA Data Buoy Center. There, the data is available for forecasters to use as another tool for tracking a growing hurricane. In Miami, Florida, the big computers at the National Hurricane Center crunch the collected data and combine it with information from satellites and other sensors. Based on their understanding of Gustav's vital statistics, they issue a prediction. The storm will hit Cuba with force and then head for the Louisiana coast. But hurricanes change and mutate relentlessly. Monday's forecast can be meaningless by Tuesday. Taking no chances, on Sunday, August 31st, the mayor of New Orleans orders the entire city to evacuate. Gustav is on track for a strike.
That's where the center of the storm is, and that's where it's been all day long, so it has to be heading this way.
August 2008. The hurricane hunters are flying into the heart of Gustav as it plows forward towards New Orleans. They're taking weather readings from inside the storm to find out what it's doing and what it's going to do. All hurricanes spin around a calm area of low winds at the center. This is the eye. Hurricanes are giant low-pressure systems. And this is the center of the system. It's where the plane needs to go now to get a closer look at Gustav.
You know, and it really is. It's a surreal moment when you go fly and you look at the winds down there and the water's all churned up. It's something that you normally don't see. It brings about different shades of greens and blues. And if you look all around you in the eye and you see just a wall of clouds, it looks much like it would if you were inside a stadium.
In the eye, the hurricane hunters take a pressure reading. The lower the pressure, the more powerful the storm. And if the pressure is dropping, the storm is getting stronger. Scientists have wondered why, out of all the smaller tropical low-pressure systems that form each year, so few grow up into hurricanes. The answer may lie in and around the hurricane's eye. Hurricanes begin as loose bands of thunderstorms off the coast of Africa. Pockets of hot air blow off the coast of the continent and run into them, pushing them out into the Atlantic. There, warm, moist air near the ocean's surface rises higher and higher, and colder, heavier air rushes in from all directions to take its place. But a strange phenomenon causes the whole system to spiral and whirl. It's known as the Coriolis effect, and it's caused by the rotation of the Earth.
If the Earth weren't spinning, we wouldn't have a Coriolis effect. As air flows from high pressure towards low pressure, the spin of the Earth actually deflects that air to the right of its direction of motion in the northern hemisphere. Now that causes the air flowing towards the low pressure to begin taking on a counterclockwise spiral around the low pressure, and that's how storms first get their spin.
The spiraling air pulls the storm together. Thunderclouds merge and begin to move around a central vortex, a vortex that may eventually become the eye of a hurricane.
So as a hurricane begins to come together, the air is flowing inward from all directions, so it is actually converging towards the center of the vortex. And as this air converges towards this very small region in the atmosphere, the air has to rise upward. It can't simply pile up and stay in one place. It can't move down. It has to move up. And so the storm begins to reinforce after some time.
Now, the storm begins to feed on itself and transforms from tropical storm to hurricane. The rotation accelerates. The vortex builds a towering circular bank of thunderheads called the eye wall. And it is inside the eye wall that scientists may have found the key factor that makes some storms develop into monsters like Gustav. A discovery only made possible by a NASA satellite.
One of the ways that satellite data has helped us to learn more about hurricanes is the fact that we can constantly monitor these storms from the very moment they form.
NASA research meteorologist Scott Braun uses satellites to spy on developing hurricanes.
One of the primary satellites for hurricane studies is the Tropical Rainfall Measuring Mission, or TRMM.
The TRMM satellite has the first and only precipitation radar in space. Orbiting 250 miles above the Earth, it makes 16 passes over the tropics every day, reporting daily rainfall in the entire hurricane belt. The satellite's instruments can look right through a hurricane and let scientists see the rainfall and cloud structures inside it. When they compared the storms that grew to hurricanes with those that didn't, they discovered something. These ultra-tall clouds, 11 miles high, that only appear in storms that become major hurricanes. They are called hot towers. These are no ordinary thunderclouds. And they might just supercharge a tropical storm into a major hurricane.
I'd like to draw an analogy between the engine in a car and the engine that the hurricane is. In the car, we have cylinders, and the cylinders are where the work is done inside the engine. We're taking fuel, we're combusting it, we're releasing heat energy into that engine. In a hurricane, each individual cylinder is a giant thundercloud.
And the fuel in this engine is the heat released when warm water vapor rising off tropical seas condenses into thunderclouds. Big thunderclouds.
When one of these giant clouds suddenly goes off, there is such a sudden burst of heat energy near the center of the storm, it's like stepping on the gas pedal and revving the engine up.
Heat energy is pumped up through the hot towers to the top of the storm, where some of it cycles back down the vortex, warming the core of the storm and reinforcing the storm's low-pressure eye. This draws in more air from all around and starts the cycle again.
Once you have all of these ingredients come together, you have a heat engine. You have a positive feedback loop in the atmosphere that reinforces itself. You have a hurricane.
August 2008. Hurricane Gustav churns through the Gulf of Mexico. On September 1st, the hurricane slams into the Louisiana coast, 50 miles south of New Orleans, with pounding rains and wind gusts over 100 miles per hour. Altogether, Gustav kills 94 people and does billions of dollars worth of damage. The question is, how can people counter-engineer against a hurricane like this? What does it take to stand up to nature's wrecking machine? 2008 is one of the worst hurricane seasons on record, with storms hitting coastal areas around the world.
Telephone poles are coming down, trees are coming down.
Asia, the Indian subcontinent, Australia, and Indonesia are all hit by damaging tropical cyclones. And in the Atlantic, 5 major hurricanes in as many months take 461 lives and destroy countless homes. How do hurricanes do so much damage? Can we figure out exactly how its winds tear a house apart?
Well, we can't wait until the next hurricane happens, so we had to construct a hurricane simulator to create that next event.
Meet Medusa. She's the world's largest portable hurricane machine, created at the University of Florida.
So we're looking at 4 700 horsepower Detroit diesel engines. Now these were old parts engines that the students and staff rebuilt. So these engines were actually built back in the 1980s. And at that time, they were modified to produce a lot of horsepower. So because they produce so much horsepower, they require a lot of water to cool them off. So we're actually standing on a water tanker truck, which serves as the radiator for the whole system to keep it cool.
The engines drive wind and water through 8 huge exhaust fans, normally used to pump air through coal mines.
Air is drawn into these specially tuned inlets that creates a tremendous amount of airflow.
At full power, the high-speed fans can blow wind and water through louvered airflows at the incredible rate of up to 1 million cubic feet per minute.
So we're producing almost 125 mile-per-hour winds at the exit. Ready on your mark?
Once we bring the engines up to run line, the computer will take over and start creating these intense winds, and we'll bring it up to about Category 3 conditions.
Even going full blast, the fans can only simulate a Category 3 storm. A Category 5 storm produces winds 3 times as damaging. Despite advances in construction, hurricane damage to homes is on the rise.
We're seeing structures are not performing well in much lower wind speeds than I think what most people would imagine. And this is of critical concern to the wind engineering community.
Although the test window survives intact, the hurricane-level winds still find a way to drive rain into the house.
So we're seeing a significant amount of water ingress. It's coming in through the window, through the installation, partially through the wall. We're also seeing it coming in from above through the soffits. When we have water penetrating our building envelope, all of your walls are going to be damaged, all of your valuables are going to be damaged. We could be looking at almost a total loss on the building.
Of course, a major storm can hurl debris, including entire flying roofs, causing enormous damage. Damage that is difficult or impossible to prevent.
Most people, when they think about hurricane damage, they remember Hurricane Andrew with extreme amounts of damage to buildings, total collapse, roofs flying far downwind. That's not what we're seeing today with homes built to the modern building code. But even in moderate winds, we've seen that shingles have been a problem. In higher winds, we see that tiles can be a problem. So typical damage we see after every hurricane, damage to roof covers by far the most prevalent.
Even a single roof tile can lead to the destruction of a home if the house isn't engineered to withstand it. And even the most fortified house can be vulnerable to hurricanes.
This is a standard Miami-Dade approved storm shutter, very common all throughout the Southeast. So what we're trying to understand is what happens when roof cover flies downwind and strikes another structure. So in this particular case, we're looking at tile impacts. And our big concern here is that when the tile strikes the shutter, we don't want this thing to deflect far enough to break the window. Okay, Jimmy, let's bring it up to 25 PSI, which should be about 45 miles per hour. Fire when ready. Firing in 3, 2, 1. So we have simulated 2 different tile impacts on the same shutter system. And we can see that the consequences are absolutely devastating. We've blown out the back of the window.
A shattered window can mean the end of a home. If hurricane winds can get access to the house, it can fill up with swirling air like a balloon, creating high pressure and pushing on the inside of the structure. Outside, the hurricane's winds are doing the opposite, creating low pressure as they stream over the angled rooftop.
The roofs are gabled so that they have an angle to them, and as the wind blows over the top of that angle, just like the curved upper surface of a wing, a lift force is generated. Now, as the wind comes over the top of the roof, that roof is literally lifted off the top of the house. The walls have to fall outward because they lose their support, and that's how your house comes apart.
Though national statistics are hard to come by, in Florida, The best estimate is that only 11% of homes have been engineered to withstand hurricane-force winds. Hurricane winds directly cause incredible damage to property, but they also help generate something even more destructive and deadly: storm surge. Late 2007, a storm surge wipes out whole sections of coastal Bangladesh. Less than a year later, Hurricane Ike brings catastrophic destruction to Galveston, Texas.
Everyone must evacuate or will face certain death.
The most deadly part of a hurricane is not the wind or the rain, or even the huge waves crashing on the beaches. It's the storm surge. May 2008, Cyclone Nargis, with winds of 125 miles an hour, moves into the low-lying regions of Myanmar and Southeast Asia. It's pushing a storm surge ahead of it, an enormous swell of water 12 feet high. The storm surge pushes 25 miles inland, in some areas destroying as many as 95% of the buildings in its path. When the water retreats, 130,000 people are dead or missing, and over 2 million survivors left with nothing. September 2008, Hurricane Ike is coming to Galveston, Texas. Ike is only a Category 2 hurricane, so many of the island's residents think their 17-foot seawall will protect them from the storm surge. 40% of them stay to ride it out in their homes.
I woke up Friday morning thinking I was going surfing. Walked out on my porch and looked out at the beach, and there were waves in my yard already. And I was like, oh, this is real, this is happening fast.
Peter Davis is the head of the Galveston Beach Patrol. When Ike landed, he rescued stranded victims caught off guard as the ocean poured in and flooded every inch of the island.
People just never really expected that water would come up into a lot of these areas. I mean, we've just never had it before in our lifetime.
Really, really bad here, folks.
Just how does nature engineer such a powerful storm surge? What makes the sea rise up and flood everything in its path? The low-pressure system in a hurricane's eye exerts such a strong pull upward on everything beneath it that even the water level itself rises slightly as the eye passes. But more importantly, the winds spiraling around the storm's center push ocean water into waves that pile up on one another.
The storm surge is just the stress of the wind moving over the water for many, many hours, sometimes days. And this piles up the water into a giant dome. That dome spins beneath the eye. This is where the winds are strong, so this is where the water is going to be at its highest elevation.
As it approaches a long, shallow shore like Galveston, the dome builds even higher until it either hits an obstacle or breaks, sometimes miles inland, flooding the land with ocean water. Ike's winds were only Category 2 strength, but its enormous size caused a 12-foot storm surge and 20-foot waves that completely overwhelmed the island's seawall, with devastating effect.
Yeah, I think you can see some of what the storm surge can wreak here with the debris that you see and how it just moves everything in its path. This is water that rose just during the time of the storm, got inside the homes, would actually lift up furniture off the ground, and then as that water receded back out, that furniture was just slammed against the inside of many of the homes, destroying a lot of the inside walls.
All over Galveston, ordinary household items became wrecking balls, leaving almost 5,000 families homeless. Hurricane Ike may have leveled the island, but it also destroyed itself in the process. Within hours of making landfall, there was no Hurricane Ike. The storm system weakened and eventually rained itself out over the U.S. and Canada. Like any machine, when a hurricane runs out of fuel, it sputters and dies.
The final act of a hurricane is its dissipation. And what really shuts down the hurricane heat engine is that you've moved it away from its supply of warm ocean water. You've taken away its source of water vapor, you've taken away the fuel tank, the engine has to start spinning slower, and it begins to rev down.
Each new hurricane helps scientists understand better how the storms are made and how they work. But hurricanes are closely linked to our climate and atmosphere. If those things are changing, does that mean the forces that build and drive hurricanes are changing too?
The weather is definitely worsening.
Ike was just one of 5 major hurricanes in as many months, the first time that has ever happened.
The bricks are coming down, the wood is coming down, the cedar is coming down, signs are coming down.
In fact, 2008 was the 10th year out of the last 14 with above normal hurricane activity. Is this a preview of our future? Atmospheric scientist Greg Holland is convinced.
I personally think that there is little doubt there's going to be more intense storms. The intensity is going to go up. The big question is it going to go up by 5% or 10% or 15%? And that's the question that we don't have a good answer on at present. So it's not like we're expecting the intensity to go down. We're expecting it to go up, but we need to know by how much.
Chris Lancy at the National Hurricane Center disagrees.
I would not think that the changes that we're seeing today to global warming that are impacting hurricanes as being large. I would see that they're a very tiny, perhaps not even measurable amount today. And then when we look at the numbers of storms, frequency, the storms may actually go down. And that's because in the future, it looks like there may be more of the wind shear tearing apart storms.
The controversy leaves scientists asking, will hurricanes be more intense in years to come? Are they already getting stronger? One team of scientists is trying to predict the future by digging into the past.
Well, we're heading down to Salt Pond. It's a pond right behind a barrier beach here on Cape Cod.
Jeff Donnelly is a scientist at the Woods Hole Oceanographic Institute. He's a kind of severe weather archaeologist, searching the Earth for the artifacts of hurricanes past. He's looking for patterns that could help scientists answer an important question. Will a warming global climate mean more hurricanes?
There's a lot of debate in the scientific community about global warming and whether we're actually impacting the frequency and intensity of tropical cyclones. We struggle with that debate because there's not much data. We've basically got a very short instrumental record that, and if you just look at the satellite era, is only going back a few decades. What this work is able to do is actually extend that work from decades to century and even millennia.
When a hurricane produces a storm surge that floods coastal areas, it picks up sand from the beach and moves it inland. Some of that sand settles to the bottom of nearby ponds in the wake of the surge, leaving the hurricane's fingerprint behind. The pond bottoms build up layers of sediment each time a storm passes through, leaving a detailed, long-term history of hurricanes. By looking into the sediments, Donnelly's team can tell how often hurricanes have occurred in the past. It just might help predict the future.
Vibracoring involves vibrating a tube into the sediment.
The sampling device, called a vibracore, works by cutting into the mud. A hollow tube vibrates back and forth, about 4,000 times a minute.
So the idea is that it'll effectively liquefy the outer millimeter or so of sediment and just let this thing go through like a hot knife through butter.
The tube penetrates the pond floor, and Jeff and his team can pull a cylindrical sample from the bottom of the pond.
We haven't gotten any radiocarbon dates yet, but I guess that we're probably looking at 2,000 years, something like that, the total record that we've recovered.
Core sampling is always a gamble. The team never knows what they have until they slice the sample open and get a good look. The good news is, the sample is very clean.
This particular site is deep enough that the sediment doesn't get disturbed by the critters. And so, it's basically a time machine. As you go back down the core, you're going back in time, like a tree ring, so you can count through 1, 2, 3, 4, and actually count through seasons there.
Can this core help illuminate hurricane history?
The records that we're able to reconstruct are the most extreme events, the Category 3, 4, and 5 hurricanes, because they leave a record just about everywhere. And what we're able to do is then look back in long time scales and see, how has the activity in these most extreme events changed through time? What kind of climate forcing may be responsible for those kinds of patterns.
Some of the sand layers are too thin to pick up with the naked eye, but Donnelly has the right tool for the job, an X-ray scanner.
If you have a really thick, dark layer, that's likely to be sand from a hurricane. This line here might be an indication of sand, a sand layer that we might want to further study to test grain size, or we could do carbon dating based on these events to see how old they are.
The team has studied dozens of samples from the Yucatan in Mexico all the way up the eastern seaboard. They cover thousands of years of hurricane history and show cycles of activity and calm.
It appears that there are intervals in the past that were quite active, at least as active as today. One of the intervals is between about 2,500 years ago and 1,000 years ago. It was pretty active. And then around 1,000 years ago, the activity basically dropped off to almost nothing. There were very few events between about 1,000 years ago and roughly 300 years ago. And then the recent active interval that we're currently in actually started about 300 years ago.
So is it man-made global warming or some other trend that accounts for the increase in hurricanes? The answer might be both.
There are natural climatic variations that are able to force changes in hurricane frequency and intensity aside from whatever humans may be doing. So whatever we're doing is kind of superimposed on whatever the climate system by itself is able to do.
Whether man-made or natural, will climate change bring warmer tropical seas and therefore more powerful hurricanes? To find out, a team of researchers is using one of the world's most powerful computers to help see decades into the future.
Will there be more Katrinas? Will there be less Katrinas? Will they come more into the Gulf of Mexico? Will they come more up towards New Orleans? That's the questions we're trying to answer.
At the National Center for Atmospheric Research in Boulder, Colorado, scientists are using supercomputers to help figure out if global climate change will affect the intensity of future hurricanes.
We are now pretty well certain that the oceans are going to warm up. And there are very good theories out there, and they say that you can expect something like about a 5%, maybe a 10% increase in hurricane intensity. The big question is, how does that get distributed amongst the actual storms?
An increase of 5 or 10% in low-level Category 1 hurricanes may not be all that noticeable. But the same increase at the Category 4 and 5 end of the scale might mean many more Katrina-type storms in the future. Only a powerful supercomputer can account for the many variables that affect how and when hurricanes form.
This supercomputer system is what we affectionately call Blue Fire. It's ranked the 30th fastest supercomputer in the world. It consists of 11 cabinets. Each cabinet contains 12 compute nodes. Each compute node has 32 processors. So the total capacity of the system has 4,000 processors and performs 76 trillion operations per second.
The team needs that computing power to simulate the entire world's climate and run 3 smaller, more detailed models that focus solely on the Atlantic hurricane belt. This allows the team to zoom in on how different climate conditions affect the formation of individual future hurricanes in areas of the Atlantic.
What we've done is we've said, why don't we take the best of both worlds, and we've taken the climate model and we've married the weather model inside that climate model.
Using the years 1995 to 2005 as a base, the team feeds in all the variables that factor into hurricane creation. The hot winds blowing west from Africa, meeting huge thunderclouds in the Atlantic that spin over supercharged warm water, which feeds rising convection. The computer turns all these factors into equations, calculates them, and runs the program decades into the future, until suddenly, the simulation starts to bring a hurricane to life. Small cloud clusters appear. The warm water fuels the creation of the eye and eye wall. Winds start to twist around the eye. They merge into a familiar shape. The computer generates a virtual hurricane, something nature engineers in the real world more than 50 times a year.
Ah, yes, that's really good.
The computer indicates that the year 2046 stands out as an intense year for hurricanes. If the planet continues to warm, as many scientists expect, the model shows summertime oceans will supercharge storms.
In this particular time, on the average, the temperatures would be about 1 to 2 degrees Fahrenheit higher than they are now. It doesn't sound like much, but that is an enormous amount of temperature difference for the oceans, which are normally not changing very much at all.
The storm looks to be huge, a Category 4, bigger than Katrina when it made landfall.
It's showing us that even though this simulated hurricane is a long way offshore, it's already raining on the Louisiana coast. The winds are already picking up on the Louisiana coast. And if you're around in 2046, this would be a really good time to be moving out of your house.
The project continues, but the model could be a warning that the next 50 years will bring more Katrinas, and worse.
Based on this and the initial analysis, it looks like we are actually seeing a very large increase in the number of Category 4 and 5. It's going to be a 5, 10%, maybe a 15% increase in intensity.
This conclusion is not shared by all scientists, but to this group, the data suggests that nature will build stronger storms in the future and present a growing threat to the millions living in the prime hurricane zones around the world.
It's already too late to mitigate some of this. We have to adapt to some of it. People should really seriously think about whether they're going to build right down on the seashore. It's a lovely place to be until a Category 5 comes past.
For all that we know about how hurricanes work, there is still mystery in how these monster storms form and develop. And as science races to reveal the workings of storms past, present, and future, every hurricane season will bring more of these awesome and devastating storms to our shores.